Ладно, проверите, да, что мы в эфире с вами, но, конечно, теперь видно плохо будет, но зато у нас конспект лекций.
Ну да.
Ладно, я думаю, что...
Ну, да, тут,
Ну, я буду, да, говорить словами, да, так сказать, все, кому надо, посмотрят уже на записки лекций. Ладно. So, okay, so in previous class, so today we shall just continue a discussion of different and discriminant. Yeah, and so as we have noticed, yeah, so let us recall what is different. So we have introduced, yeah, so as usual we have A that is contained in B, yeah, so where B is an integer extension of A, and both of them are integrally closed in their fraction fields. And also the extension of fraction fields is finite, supposed to be finite. And we have introduced the dual object by considering B star the set of integers of B such that so the set of integers is taken in the corresponding fraction field such that trace of B tilde sits inside belongs to A. Yeah, so for any B tilde inside B. Yeah, and we considered different. Yeah, so notice that clearly B star contains B, yeah, and it is B module. So this is B module, and also we have noticed that it is finitely generated B module. So it is fractional ideal, and we can consider different, so B over A, so such that it is just the inverse of B star, and the reason of introducing it in this form, of course, so that it is now ideal in B. Yeah, so ideal in B. So yeah, so we have noticed that we are different. One can characterize the following: that if you have A inside, so it is fractional ideal for so A is a fractional ideal. For K, yeah, so considering it, so fractional A, I would say A ideal, yeah, so meaning that it is a module, finitely generated A module in K, and the B is a fractional ideal for B. B ideal. In L, you have characterization, we have characterization, so that was proposition, we can characterize the property that the trace of one of them is contained in the other. So the trace of B is contained in A. So this is a complicated condition from the viewpoint of check. Yeah, so we have to, at least it is not clear how to check it, but this can be checked in terms of ideals. So I mean, so you can, so this, in order to check this, yes, so of course you should take the generators over A, of B over A, and check that this trace belongs to A. But notice that you can take, instead of this, we can formulate this purely in terms of fractional ideals, multiplication by fractional ideals. Of course, we pay the price that we think that we have already calculated different. So all complexity is in calculation of the different. And the benefit that this condition can be written in terms of fractional ideals, and notice that it is linear, somehow linear with respect to ideals itself. Yeah. So then I want to I want to discuss how different is changed than the extensions. So that's the reason for that is that if you want to use some, if we want to prove some properties of different, some special properties, you can reduce them for some extension and see how they look there. So suppose you have M that contains L that contains K, and here you have corresponding rings of integers. So A is equal to the fraction field. So fraction field will be just K. A is integrally closed. And C and D are rings of integers. Rings of integers over E. The full rings of integers, so you take all the elements that are integer over this. So then you can calculate the difference of C over A. So the largest of the large extension is just a product of two difference. So that D of B over so to say yes. So D of C over B times D of B over A. So where we think of this as the product, pairwise products of elements, and we generate the ideal after that. Yeah, so notice that these are ideals in C. And this is ideal in B. Right?
Is this a fraction ideal?
Different is usual ideal. Yeah?
Oh, okay.
I mean, just because, so for this reason, yes, so let us recall that the B star itself, yes, so the dual object of B, it contains B. So when you invert ideals, you invert the inclusion, but B inverse is equal to B. Yeah? So if you have just ideal I and J, I that is, contains J, then I inverse is contained in J inverse just by applying definition and if this property that B star contains B transforms into B star inverse is contained in B inverse, which is B. Yeah? So that really makes sense. And it is B module, yeah? So that it is clear that from the definition that it is finitely generated. Yeah, so it is B module, but yeah, so actually, right. So we even do not need to. So I have said that it is finitely generated B module, but I mean, in order to notice that it is finitely generated B module, it is not needed. This condition is not needed, just because taking inverse is formal operation and formal reverse inclusion, so you get that the universe is ideal in B, so it is, and we have learned that the inverse of ideal is fractional ideal. Yeah? So that's why it is. So here we do not need it. So this follows from. It follows from this one. If I in B ideal, then I inverse is finitely generated over B. So yeah, so that is. And notice, yes, so that here you have two ideals over C, and the one you just generate the further the idea. I mean, if you of course even so you take all possible products and take their sums, but since D is ideal in C, what you get is ideal in C. I mean, we do not generate an ideal, you just can take all possible products and their sums. So this, yeah, so let me prove it. So the proof will use the previous proposition. Yeah, so meaning that, of course, just if you want to check that ideal C is inside the different, yeah, so in the inverse of different over C over B, yeah, it happens, so this is fractional ideal. Yeah, so if you want to check it, it happens by previous proposition. Condition for some fractional ideal for C. Yeah, so this happens if and only if trace of M over L of C sits inside B. Yeah, so we multiply by B inverse by this D of B inverse. I mean, it is funny, yes, so when that you are just multiplying by inverse of the different, yeah, because yeah, it is just multiplying by B star, yeah. Yeah, but we have introduced difference, so this formula, of course, for B stars, but written in terms of difference, and of course this also looks funny, yes, that C so this B inverse, because this is against C inverse, but with respect to, but it is better to use this notation because we have not introduced special notation for B dual. Yeah? And with respect, because you have different C's, you have C dual with respect to A and C dual with respect to B. So this, yeah, so this trace, yeah, so we multiply it, so you get D of B over A inverse, so you multiply by the trace, and trace is L linear, yeah, so this is, so it sits inside D of B inverse, so this is A linear, L linear function. So you get that. Yeah, so you can put it inside and write down the trace as the composition of traces. So we just move this thing inside the trace and notice that also that trace of yes, yeah, so we take trace of L over K. Yeah, so we apply this trace, and this will result into trace of ML. So we are putting different inside. Taking trace, further trace from L into K, and this is a subset of trace of L over K in a different inverse of B over A. Yeah, and of course what you see here that so you have it precisely taken the B dual, so this is B dual over A. So the trace sits inside A. By definition. And yeah, so then you this we get so we put that this thing is just a trace from M over to K, and we get that trace of M over K of D of inverse of B over A. Yeah, so better to write down inverse as the operation. So you multiply it by C, and this sits inside A. So this is equivalent. So using criterion, again for ideal B, yeah, so and for A, you see that this is equivalent then saying that D of E over inverse C sits inside the D of C over A inverse. So this means that C sits inside D over CA inverse D over B A. And this implies that, yeah, so from yeah, so notice that C is C was the thing from different. Yeah, so let us recall that C was from inverse of different. So we can put, so C is equal to different, inverse, and we get that B of C B inverse sits inside D of C inverse times D of B A inverse. And on the other hand, since if you apply trace,
Спасибо за зум, потому что плохо видно, что
хорошо, спасибо.
интересно. Сложнее сейчас
То, что мы не здесь включали, это правда, потому что мы
Мне
включали.
ответственные за...
Вот это не работает?
Нет,
Да, мне сказали
уже где-то
ответственные за
недели две.
распределение трансляции, что вот это не работает.
Ладно, тогда покажите.
Ну ладно, хорошо. Спасибо, что пришли. Yeah, so this of course yeah, so this tells you that you have this kind of inclusion and the opposite, just taking into account opposite inclusion. So taking into account opposite inclusion. We get that so we get the required inequality. So that we have C over A is equal to D of C over B times D of B over A. Yeah, so C over A is, I mean, you just take, so opposite equality is just C over A, it contains the product of C over B and B over A. Just. By definition. So this was, I mean, that we're checking was a non-trivial check. And what is the aim of calculating different? Yeah, so that was the following. So recall that if you have so this is spectrum of B, this is spectrum of A, and we were considering the ideal P, and the ideals line covariant, so beta 1, beta 2, beta k, and we have considered P beta, that is extension of ideal P, and you have the corresponding decomposition in the product of the corresponding ideals in beta with multiplicities. And why we are just considering different, that we want to keep track on, so we want to find bound on EI. Via knowing the different. Yeah? So we are considering. Yeah, so this will be, of course, a product. So the claim is that more or less this thing is just a product. I mean, in good cases, this is just a product of ideals where EIs are not equal to 0, but and you just write down EI minus 1. So just I mean, let me put it in parentheses. So I mean up to details. So different B of A is just the product of beta I, EI minus 1. So meaning that, so this of course, where beta, so better to say E of beta, where beta belongs to spectrum of B. So notice that this is just the product of ideals where ramification occurs. Yeah, so just and actually, so the claim is that this thing is divisible by this ideal. So this bounds. So so of course, what you see here. So if E beta is equal to 1, there is no input of this ideal in this product. So what takes into account only ramification points here. Yeah? So just what should be written actually that different contains this idea. Yeah, contains this ideal, and this is contained opposite inclusion. So it can be it is contained. So the up to details. So meaning that if you write down different and the product of BIs, they have larger multiplicities than this ramification matrices. And corollary, of course, corollary that the set of ramification points is bounded. I mean, it is so since you are writing down this as a product of now BIs for some multiplicities MI, so the set of ramification points is bounded by ideals, that meaning that just that if beta, so if E beta is not equal to 1, so that is larger than 1, so beta has non-zero multiplicity, indifferent, and this is just fixed fractional ideal. It doesn't depend on it. Okay? So it, I mean, on the point you are taking here. Yeah, so I mean, it doesn't depend on the choice of the point where you consider unification indices. And notice that ideals are decomposed since there is only one option, so lying over ideal is just it is a condition, yes, of given ideal beta, and then you know that beta intersection with A is just a prime ideal. Ah.
Что случилось?
Да, чего-то. О. О,
Ну там почему-то оно...
а я вот так сделаю, сверну. Еще раз сверну. Не обманывай.
Не, он почему-то его не хочет открывать. Я боюсь, что это можно починить только закрыв и открыв заново.
Мгм.
Кажется.
А я могу новый файл открыть, да?
А, ну,
Да, какой-нибудь. Сейчас. А, это PDF. О, получилось. Нет, не получилось. Так, это, конечно, интересно. Что делать? А, может
вот
это?
закрыть.
О, все, я могу, да, обманули его.
Что вы хотите?
Я хочу окно открыть. Ну, как бы, оно не окнами, значит, открылось, да? Получается.
А что такое окно?
Ну, вот, ну, в смысле, что в одной программе
А,
оно
Не
может...
несколько вкладок.
А?
Не несколько вкладок в одной программе, несколько окон.
Ну да, вот я как бы не понимаю, он ее открыл несколько раз, саму программу, или как несколько, ну, вкладок, да? Вот. О! А, у меня же он... Вот проблема в том, что я его не сохранил. Вот, поэтому... Точная справка. Сейчас вы... Да, он ее как приложение. Ну, в смысле, как новое окно. Тут может какой-нибудь полноэкранный режим есть или что? Это... Да уж. Ну, да, давайте я просто новый файл попробую открыть. А этот сохраним как бы. Вот оно окно. Если я беру закрыть все окна, он мне предложит сохранить, правильно?
Наверное. Будем надеяться.
Ну, у меня есть файл этот, так что это. Так,
Да.
сохранить. О. Мы его обманули. Так. Так, сегодня 16. Так, недавнее у нас есть тут. Может это... Вот. Документы как раз он появился. Ну что? Ура! Так.
Теперь, да, победили.
Да.
Теперь действительно победили.
Да. Вот. Yeah, so what you see here, so that this gives, so since different is fixed ideal, this gives bound on ideal. And if you want to do calculation, so а где тут увеличение странички? Size. Я
Мне
просто...
кажется, он в нижнем правом углу. В нижнем правом.
Точно, да, правильно. Вот. Yeah, so, потому что когда стоишь вплотную к этой доске, еще вообще ничего не видишь, да, то есть это как бы о том, с какого расстояния нужно телевизор смотреть оптимально. Вот, yeah, so if you have, let me discuss calculation of different, and that will be important for you because for the exam problems. Yeah. So notice that so consider elementary extension. Elementary extension. Yeah, so such that alpha is so meaning that B is just A of alpha. So this is of course elementary extension of fields. Yeah, and we can take element in order to so it works for integer polynomials. At least you should know that B has alpha as a root of integer polynomial of. So alpha is a root of f over, so the polynomial over a. So notice that here it is not so clear that if you add the root of one polynomial, then you get that all in a ring of integers b. And this we will discuss later, that such actually, so notice also that if, for example, you have, so sometimes your extension is not generated by one element. And just on next part of the lecture, I shall discuss the conditions that, under some conditions you can assume that the extension is generated by one element. So, but now we just consider abstract problem. So now we have a basis for, so basis alpha 1, alpha square, etc., alpha n minus 1. And our aim is to find dual basis. Yeah? So aim is to find the dual basis. With respect to trace map. So how we are doing it? So notice, so let me just say that, so suppose alpha 1 and alpha n are roots of, so alpha 1, etc., alpha n are roots of f. So initial, of course, alpha is just alpha 1. Yeah, and of course in algebraic closure. Yeah? So you consider all possible roots of your field. Yeah, suppose also that f is a separable polynomial. I have forgotten to say this. So this is separable polynomial. So that means that the derivative is not identical to 0 of this polynomial. And then I claim that, so then I claim that there is the following formula. So let me formulate this proposition. That you have a sum of n from I equal to 1. So let us write the following polynomial. So here we write f of t divided by t minus alpha I. and write down 1 over f prime of alpha I multiplied by alpha I r, and this is t to the power r. So this formula holds for any r. And notice that simply this is just formula. So let me reduce it to recall that this is just Lagrange interpolation formula. Just for function, g of t equal to t to the power r. Indeed, so how does usual way to write? I mean, this way to write it, I mean, this is simply a Lagrange interpolation formula, but it is the way how you can write it economically. I mean, but let me recall it how it really looks like, and we shall see that this is precisely what we need. So this we write it down. So upstairs. So this is the formula that tells you how to interpolate any function by polynomial having the same values in the point of the function. So you get rid of t minus alpha I upstairs. So multiply by the value of the function, and this is just the course. If g of t was polynomial, then so let me just then of degree less than, so if a degree of t, g is less or equal less than the number of points, so number of roots, so a number of, so less than n. Yeah? So r here also should be strictly less than n. And yeah, so you divide here, and you divide by the same product, but where we substitute precisely alpha I. So you omit the bracket alpha I minus alpha I. And this is alpha I minus alpha n. And of course, if so this is elementary how to prove it. You just substitute corresponding root alpha I, and you see that if your product contains alpha I, then it gives you 0. If you omit alpha I, then upstairs you substitute alpha I. So this fraction becomes 1, and you get the corresponding value of the function. Yeah. So, and notice that simply upstairs, so if you look upstairs, yeah, so you can view this upstairs polynomial as just f of t. So this is just f of t divided by t minus alpha. Yeah, where alpha is the corresponding root. And this thing is it is well-known formula. It is just the value of derivative in the product alpha in alpha I. Yeah, the reason is that if you take the product t minus alpha I and take derivative of it, Yeah, so by Leibniz rule, it is precisely the sum of these brackets, but this is uh, yeah, so this is t minus alpha 1. This is the sum over I, where you substitute t minus alpha I, and you just differentiate t minus alpha I. So you throw it away, the one factor. So you, by Leibniz formula, you just throw away one of the factor. So by Leibniz formula. And when you substitute here alpha I, then of course, this is just only sum of the remains where you have thrown away alpha I. So you are just writing down alpha I minus 1, so the I summoned is thrown away, and alpha I minus alpha n. So that is precisely what is written, just what is written in our formula. So this is if t is just the power of r, then you are writing down alpha I in this power. So let us notice that this can be viewed if you take the. So I want to write it down in terms of trace. So notice that you can pick up. So if you have sigma, just all possible inclusions of k into k bar. So inclusion is parameterized, is defined by the value on the root. Yes, so you have one generating element by applying sigma of alpha, which is also a root of f. So when you this sigma runs through all possible roots. So just we can write down the trace. So formally we can take a trace. So if you apply trace to the polynomial in some extra variable, you just I mean by our agreement, let us apply it only to coefficients when the variable is just not specified. So let us apply trace to f of t divided by t minus alpha 1 over f prime of alpha, and this and alpha r. Yeah? So this is precisely the sum over all possible inclusions of k into k bar. So the trace is just applying sigma to the corresponding element and taking product. So trace of beta is just sum of over sigma k bar. The sum of sigma is sigma applied to beta, and this is just the sum where you are writing down f of t, t minus sigma of alpha 1 over f prime sigma of alpha applied to alpha in the power r. And this is just the formula that with alpha i's, of course. Yeah, so this is f of t minus alpha I. And such sum is just, you know, that it is equal to t over r. Yeah? So this is equal to t over r, meaning that we have found so if what we have found, so if you denote it by corresponding alpha I tilde, so if you put alpha I tilde to be f minus t. Yeah, so notice that what does this means from our point of view? So you have taken, so this f of t is just what I have written. So notice that this is polynomial. So in our field, so with coefficients in, so you have t n minus. So it is of degree n minus 1. So here you have beta n minus 1. It is not integer polynomial. So this gives you etc. plus beta 0. So let us omit alpha r. Sorry. So I'm writing down like this. What is the benefit? So beta i's are, notice that beta I, so the claim is that first of all beta i's are elements from they are the following. So if you write down, so beta i's are of course the elements of the field L, but notice that they have two parts. So if you look at f of t, t minus alpha, then I write the same formula, but with b n minus 1 t n minus 1 plus b0, and this is not coincidence. Yeah, so beta i's I mean in the notation, because beta i's are just in b. So the claim is that beta i's are inside b, and the reason for that is very simple. Is so that you just have the corresponding equations. Yes, so if you write down f of t, so you look at the corresponding coefficients. And here you write down t minus alpha. And you get that, so you get the following, so you get the following equations. Yeah? So that, first of all, what is alpha 0? Alpha 0 is just beta 0 times alpha. Yeah? So just if just you have 1 is equal to b n minus 1 plus alpha times b alpha bn minus 1 times bn minus 1 plus alpha times bn minus 2, yeah, etc. So you see that over just if this no, that was mistake. Yeah, so the highest coefficients is that was my confusion. Yeah, so you see that beta n minus 1 is just 1. Yeah, so a n minus 1 can be written as what? As it is b n minus 2. This is so this is obtained by multiplication of degree Tn minus 2 by t minus alpha times beta n minus 1, yeah, etc. So you see that beta i's are just elements of A of alpha. Bi's are just elements of A of alpha. So they are also integer. Yeah, so also integer elements. So what is standing here? You have some integer elements divided by the same. So beta i's now are just obtained by dividing bi's by the same value f prime of alpha. So you want to so notice that the claim is that beta I is precisely dual basis. So first claim that beta I is form dual basis. Beta I form dual basis. The powers 1 alpha, alpha square, etc. Alpha n minus 1. And the reason is precisely in the formula, because you are writing down the polynomial f of t. F of t divided by t minus alpha times 1 over f prime of alpha, and this is g of t, so the polynomial with coefficients in beta, and what you are writing down, so let me write it again, beta n minus 1, beta n minus 2, yeah, so what you are doing, you are multiplying g of t by alpha I r, yeah, and take the sum, yeah? So that is precisely over I, which is just a trace of g of t alpha r, and this is t to the power r as we have calculated. And this is precisely means from the viewpoint of beta I that trace of, so since this is just, so this is a sum of traces of beta n minus j. Yeah, so maybe bj beta j times alpha r times t to j. Yeah, so this means that precisely that this is the answer is non-zero. So this means that trace of beta j is equal alpha r is equal to 0 if r is not equal to j, and is equal to 1 when r is equal to j. So that is precisely, so because this is precisely this r. So this is Kronecker delta sigma. So this means that different, in order to write down different, you have to invert, so to write down d of b over a, we have to is equal to inversion, so we have to generate ideal by beta n minus 1 divided. Invert the ideal. This means that b star is just generated by beta 0, etc. beta n minus 1. This inversion of beta star, but notice that this thing is principal ideal. I mean, this is written as 1 over f prime of alpha times the linear combination of b0, etc., bn minus 1. And these beta i's were precisely, so they just if b0, etc., beta n minus 1 generate a of alpha. If you open the brackets, you will get that b's are just polynomial starting with coefficient 1. And so beta are just polynomials of degree, so bn minus 1 is equal to 1, and beta I is polynomial of degree precisely I n minus I n minus I minus 1 in alpha. So for this, this is degree 0. Yeah, for b0, it is the just when I is equal to 0, it is polynomial of degree n minus 1. So this means that this is precisely, so this is b as ideal. This is just b. So the ring b where you divide by f prime of alpha, and so this is principal ideal, principal fractional ideal. So this means that in particular that d of b of a just inversion of 1 over f prime of alpha. So this is just f prime of alpha. And now let us see that the discriminant is what is we expect. So just let us observe that we have proved that discriminant is a norm of different. Just a norm of different. When it is principal ideal, it is just norm of the corresponding ideal of f prime of alpha. This is just a product of f prime of alpha I, yes, so where I all possible roots. It is just a product of f usual norm. So we use the formula for usual norm via all inclusions. Yeah? So which is just the product of alpha I. And notice that we can open the brackets, and this is what for alpha I. This is the product of alpha j minus alpha I. Yeah, so where the product is over all j is not equal to I inside the product. Yeah, so you just this product is just taking all alpha I there is alpha I minus alpha j. Yeah? So inside you have alpha I minus the roots of f, which is alpha I minus alpha j, and the product is taken over all alpha I. Yeah, so that is so this means you take into account the root twice. Yeah. So that is a square of so that is really a product of alpha I is not equal to I is not equal to j. Yeah? Of alpha I minus alpha j. And so alpha I and alpha j appears twice here. So it is a square up to the sign. Yeah, it is a square of Vandermonde determinant. So that it is a square, so up to minus 1 and some sign. So alpha I minus alpha j, where I is less than j. Yeah? So this is precisely a square. Yeah, so this is square, and just Vandermonde determinant of alpha. Yeah. So that is the determinant of the matrix of 1, etc. alpha n minus 1, alpha 1, 1, etc. alpha 2, n minus 1, etc. Yeah? And so that is the square. So this is precisely what we have learned as a discriminant. We have taken a basis, and this is just the matrix. So we have taken a basis, 1, etc. alpha n minus 1. Yeah, and have written down. So here, if you have omega 1, etc., omega n, you have to write down it, so a different basis. You have to write down the determinant written by sigma of omega 1, sigma of omega n, etc., where you run over all sigma, all possible sigma. And here you have written 1 over n, and this substitution sigma is just substituting index alpha, so this is precisely the formula for determinant. For discriminant in basis 1, etc., alpha n minus 1. So and by construction we have learned. So this is the basis, not the general, not linear independence. Yeah. So we have just in general we have to take all possible. So now I want to make a comment on the problem that we have in class. Yes, so notice the following. So if your ring of integers is generated by, so the problem is that the formula that we are considering here, so we have to know that B is a full ring of integers. Yes, so to say that it is discriminant, we have to say that the B where you apply B of alpha, so B is alpha I, is so to write these formulas. So we have to know that B is a ring of integers. So I mean full integer. So it is algebraically integrally closed in its fraction field. In fraction field of A of alpha. For given alpha, this can be not true. And so a priori, so this calculation is, so we have calculated the dual basis, but for writing down discriminant, this calculation is void. So you can, the example is that I have given you in as the problem. And the home task is the following. So you, if you know that your ring is a full ring of integers, this is some kind of particular, this is a basis, and discriminant is well defined. So discriminant, in order to write down discriminant, you can take the basis and of the ring of integers, and you can write it down. Yeah? But if so, write down this determinant, and this is precisely the discriminant of your ring. But if this 1 alpha, etc., alpha n is not, so if B is not integrally closed, so that means that 1, etc., alpha n is a basis for B, but not the basis for ring of integers. And of course, during this calculation, we didn't use the property of the decubitus. But in order to write down norm and in order to write down this equality, we used that B is dedekind. So here we used that B over B is dedekind. Ring here. And so our calculation is correct, but it doesn't give you, I mean, if you do not have this inequality, yeah, so when this doesn't hold, yeah, so the calculation after this is correct, but this is not discriminant. Yeah, so if B is not integrally closed, so this discriminant can be larger. Yeah? Is a larger ideal. So we have generated only the part of it, and the problem really for the exam really tells you that there is a particular example where this discriminant is not generated. So this is called discriminant of the element, and this was particular example where discriminant is not generated by one element. Okay. So that is precisely the calculation that, yeah, so just because you have to consider different possible generating sets, and the problem is to find such a generating set to prove that discriminant is actually a little bit larger. So, okay, so let us make a break, and after the break I shall discuss first of all I shall discuss in which case the ring B's can be thought of generated by one element. Then I shall speak about some why completion of the rings. So why it is important to complete rings, and so maybe if time permits, I shall make the calculation for this order of the different that will tell you that really EI ramification indices really divides different. And in order to do this, you have to use actually this formula for different. So let us do a short break. Привет.
Привет. Так, ну что, помни давай. Вот это да. С первого раза согласился меня.
вы не знаете как? Увеличить.
Что вы хотите?
Увеличить.
Да, который ждал здесь.
Здесь.
Да. Увеличивается, там видно, очень
Подвинуть.
Да. Вот. Нам нужно тогда
Да.
увеличить.
Увеличить.
Вот, наверное, вот так нормально.
Ну, так, условно. Ладно. So let us now. I want to make just first of all I want to discuss how we can generate the ring of integers, and then I shall discuss what can be do for yeah. So I want to make the observations of how different is divisible. Yeah. So let me just. Suppose, yeah, so if you consider consider just I want to make some special calculation because it is really crucial, and later I shall explain how to reduce to this calculation. So consider A, it is a discrete valuation ring. And also, yeah, so just the maximal ideal will be generated by pi. And also we shall consider, yeah, so here I won't actually specify how this, by which element will, and B will be extension of A, which is also discrete relation ring. Discrete relation ring. And also we shall assume the following, that yeah, so this is discrete relation ring, so that is only one ideal lying over our fixed maximal ideal. So you have the extensions so of the field. And here you have ideal P, here you have ideal beta lying over it, and notice that since the priori this is discrete relation ring, there is only one ideal lying over P. So P times beta, P times B is just beta in some power. So I claim that B can be generated by one element. So claim that I will prove a little bit later. B can be generated by one element. and with assumption that it is still uniformizer, so it is a generator of beta. So such that. Also, sorry, I forgot to say. So also we assume that this extension is unramified. Yeah, so plus assume.
So E equals 0.
No, no,
One.
sorry.
Separate.
Not so vice versa. Totally unramified. Yeah. So assume that the extension is totally unramified. I shall explain what it is. So meaning that the number f, which is beta, the degree of beta mod b over the degree of field extensions of beta mod b of over a mod p, is equal to 1. So let me, sorry for switching into Russian. I want to comment on the translation of the word totally. То есть на русском языке total unramified это вполне разветвлено. То есть, но как бы психологически для меня это немножко, ну как бы мне это не очень нравится, потому что для меня totally это вот прям совсем не разветвлено. Вот, а вполне не разветвлено, ну как бы есть в русском языке, ну вот, как бы примерно такого же сорта перевод, но вполне может быть, ну как бы, то есть неуверенная форма этого дела, да? То есть как бы, что, ну, в целом так, но не, возможно, не совсем, да? Из-за этого у меня психологически тут, ну, по крайней мере, то, как я это слово вот чувствую для себя.
Почему unramified? То есть это
Ramified,
Totally ramified.
То есть как бы, то есть все ветвление, ну, то есть как бы вся степень расширения сосредоточена в E, да? Ну, то есть как бы, so assume that totally ramified. Totally ramified. То есть, как бы это вполне разветвлено. То есть, ну, как бы у нас, so since we have, in this case, we have only one prime ideal over B because it is discrete relation ring. So we have a degree of extension, n is degree of extension L over K, is equal to precisely E times F. And you have two opposite cases where E is equal to 1 and F is arbitrary, and F is equal to N, or vice versa, F is equal to 1 and E is equal to N. And so the claim is that B can be generated by one element such that it is uniformizer of B, such that P is equal to, so the ideal generated by P is equal to this ideal B. This is this we shall discuss in a few moments, but so these are to just this is under this assumption. It will be clear how we can. So we shall discuss how we can generate B over A for arbitrary fields. Then we shall discuss in arbitrary rings of integers Then we shall discuss what happens if this extension is better than that we expect. So when it is separable, this is of course for number field it is always separable. And if then we have to just and in the case when this is totally ramified, so when this is 1, we shall see from the construction that the generator will be uniformizer. So if generator will be uniformizer, then P satisfies, so E is equal to N. Yes, so P, so in our case, yeah, because, and this says that P satisfies the corresponding polynomial. Yeah, so the so-called Eisenstein polynomial. So Eisenstein, no, Eisenstein, polynomial Eisenstein. So let me say that P satisfies this polynomial. So then P satisfies T here. And what can be said about this polynomial? So first of all, notice that A0, so this is an element of A, yeah? And in the same time it is divisible by P. So writing down, so A0, it belongs to, it is just minus P times P. A minus 1, etc. A1, yeah? So this belongs to beta. So this means that A0 belongs to beta intersection with A, so which is P. Yeah? So you see that at least you have yeah, moreover, your all coefficients, so if you look at the corresponding coefficients, that AI are just the elements of E, and what are possible evaluations of EI. So notice that, so this means that if you see that valuation of EI is positive, so it is, so you have a uniform, so AI, valuation with respect to beta is positive. Yeah? So this implies that AI belongs to beta intersection with A, so that means that they belong to P, and P is just generated, so P beta, so it belongs to P, and in particular to P times beta. Yeah? So this means so AI belongs to P times B. So this means that valuation of AI with respect to beta, and PB is just beta to the power E. Yeah? So that means that valuation of with respect to beta is divisible by E. By Okay, so this is very important property. So let us consider the valuation of the corresponding elements, and we shall see that. So if you take a valuation of beta and valuation of AI, P, E minus I. So this is a valuation divisible by E. So this is a valuation of A plus valuation of, so let me write it down, valuation of AI plus valuation of P, E minus I. So this is valuation of the form E times Ki, where this is integer number, yeah? Plus E minus I. So precisely this one. So the problem is that so when you are looking at the corresponding elements, so when they can cancel, so they can so suppose so if you write the sum, yeah. So when you write the sum, you should see that the elements. I mean, if you have the elements and they have all pairwise different valuations, they cannot cancel. Yeah. So if you have the sum of omega with different valuations, and equal to 0, and valuations of omega I are different, then they cannot cancel. But notice that what is minimal valuation? Yes, so in order to do this, you have to consider minimal valuation. Yes, so they cannot cancel because you have minimal valuation, and then higher valuation cannot. I mean, there will be one element that will have minimal valuation, and the other elements cannot cancel it. Yeah, so you cannot. So the valuation of the sum will be precisely non-zero, minimal valuation of minimal. So you see what is minimal. So you see that this valuation is at least larger than E. Yeah? So if you have so first of all, so just if AI is at least so either they are larger of E or the I mean the valuation of these guys that are intermediate, they are different from a valuation of E.
So whether PE plus A1 PE minus 1, so isn't the last one should be AE?
Что говорите? Вот
Не, вот у нас уравнение вот это p в степени e плюс a1 p в степени e минус 1 и так далее, а там у нас...
извините, ну e минус 1.
Все, окей, да. Ага. Почему тогда вообще считаем ai p в степени e минус i? Если у нас не такое...
Ну, да. Ай, да, потому что, ну, как бы, просто так, ну, как бы, там, а за что? Просто так. Детский мультик какой-то был. Вот. Добрый. Так, ну, как бы, So let us look what is minimal possible degree. Yeah, so the reason is that, yeah, so what is possible minimal? So you have the sum of points, so you want to ask what is minimal of omega I. So it can happen that, so already you know that minimal is less or equal than, so minimal valuation of omega I with respect to beta. So of course you know that it is at least less than equal to p to the power e, yeah? So which is e. So of the first sum. Yeah? So this means that if this minimum attains on this element, if it is of the form, so if this valuation
Who's omega I?
omega, so you have a sum, so the sum of the terms, I mean, just let me call it bi, I mean it is just this IPR, so I mean just let me. So if you take minimal valuation of AIPI, yeah, so if it is less, so first of all it is less of less or equal. So this is minimum all over I. So in particular I can be. Yeah. So this is at least less than E if.
Why is it less than E?
Because this is the first term of the equation.
Yes, and why is the whole evaluation?
They are all, yeah. So I say that they are all different.
Yes, okay.
So what can happen? That first of all, let me assume that A0 has valuation. So I want to prove that A0 has valuation precisely E. I want to prove that it is a Eisenstein polynomial. So let me call let me write the claim that I want to prove. So claim is that A0 valuation with respect to beta of A0 is equal to E. So precisely E. So why this is true? Because if your valuation is minimal, so assume that A0 is not equal to, assume that valuation of A0 is not equal to 2E. Yeah? So that means that A0 cannot, it is valuation divisible by P. So it should be larger. So notice that all possible, so all just AIPI has pairwise different valuations. Valuations. So because they are of the form of EKI plus I, so they are different even modular I, even modular E. So they are different modular E when you consider them as integer numbers. And you see that this means that if you consider minimum, so they are all different. So if the first is different with the last, they are all different. Because I mean, among, so if you take the evaluations, so first term, so let me write down evaluations of summons. So maybe it is better to say like this. So consider evaluations of summons. So let me just of summons AIPI. So first summon will have valuation E. The second summon will have valuation K1E plus 1 plus E minus K n minus 1 E minus 1 E. So plus E minus 1, etc. You are writing down K, J, E plus J, yeah, and etc. You are writing down valuation of A0. A0. Okay? So for valuation of A0 is just a valuation of the form E times K0. Yeah? And what can happen if so if first one is not equal to the last one, so if E is not equal to K0 E, yeah, so then all numbers all numbers are different here because just all numbers are different. Pairwise different, yeah, because so the first of them has different. Just first E etc. K J E plus J has different residues modulo E. Modulo E. And the last one has last one has different residues. With Kj I plus J and EK0 is not equal to E. So all numbers has different all numbers has different valuations. So so this means that valuation with respect to beta of the sum is equal to minimum of the valuation is minimum along I of the valuation of the factors. So this has so this sum is not zero. So sum cannot be zero. Because we assume that sums are different, so they are non-zero a priori. So this means that then we come to the contradiction. So we see that A0 has precisely valuation E. So this means that we come to contradiction. and so this means that valuation of A0 is precisely E. So this means that A0 belongs to P and not to P squared. Yeah? So this is a Eisenstein polynomial. And now just all other elements, if you, so the polynomial should be reducible, and this means that if yeah, so so the reducibility implies that the polynomial has that all coefficients are actually so all i's. I mean, if they cannot. So in order to so you see that they cannot have smaller. So notice also. So AIs cannot have smaller valuation. So AI PI cannot have smaller valuation than P. So cannot have smaller valuation than E. Yeah, because otherwise they cannot cancel together. So if they have smaller valuation than P, so otherwise.
Yeah, but if they have larger reasons, they also can't cancel each other.
If they are larger, they can cancel because I mean because you are canceling PI with A0, and the difference can have terms that have larger valuations than A0.
Yeah, that's true.
And so you are writing down you are writing down PI, and you are writing down A0. So here A0 can be written as PI plus. So we're saying that it has valuation divisible by PI. So it can look like B1 plus PI plus 1, etc. as the series. And the end of the series can cancel the corresponding elements. So, but also that they cannot have smaller valuation than P, so otherwise the minimum, so minimum of AI will be obtained on only on one element, so will be obtained on one summon. Since of the form AI PI where AI is not equal to 1, yeah? Yeah, so E is not I is not 0 and E. And just since it because they are pairwise different, so they cannot cancel. So they cannot cancel. And this implies that AI have also positive valuation. So this implies that the valuation of AI is positive is bigger than 0. So it is divisible by E. This is about Eisenstein polynomial, and let us apply it to calculation of different. So if different of b over a is just you have to take the polynomial and calculate it in p. Yeah. So the derivative. Yeah. But derivative, yes, you are writing down it explicitly. It is p minus 1 plus e minus 1 times e minus 2. So just коэффициент не написал. And the last coefficient is a1. Yeah. So with degree 1. Yeah. So notice that again minimum. So these guys, yeah, so has they have so since AI have valuation divisible by e. So you can have two cases. So this means that valuation of these elements of the form AI is pi is at least larger or equal than ki e plus. So I mean the valuation of the summons. Yes, so of the full summons were also. Notice that we're speaking about numbers as if we're speaking about when k contains integers. So integers can have positive valuations as well. From the so for example, if we have integer numbers and for valuation you start with p and then you localize to obtain discrete valuation ring with respect to p, then it can happen that these coefficients are divisible by so here you have e minus 1 and here you have I. So you take valuation of beta with respect to I, and this is bigger or equal than valuation of ki plus I minus 1. So you see that minimum, so this ki are strictly bigger than 0. So this is bigger than e, strictly bigger than e. So minimum is larger of this valuation is larger, bigger or equal than e minus 1. And of course, if e is not in the characteristic, if e is not in the ideal p, then the minimum is obtained on the first factor. So that this implies that minimum of the valuations of summons.
So if you
is equal to e minus 1 and obtained on the element on e times p e minus 1. So otherwise it is not clear on which, so it is obtained on one of the elements because they have pairwise different valuations, but it is not clear on which of them. So otherwise, it is not clear. It is obtained on one of the elements, on only one of the elements, but not clear on which of them. So you see that in particular you see that valuation is so in for example so if characteristic doesn't divide E, so if characteristics of the residue field does not divide E, this implies that d of b valuation with respect of beta of d of dA is equal to E minus 1, so otherwise so it is valuation is larger. Just larger. And this means that your factor, and it is not clear, so if it is strictly large or not. But what is important for us that this gives you bound, so the existence of different gives you bound on the size of ramification locus. So this bounds. So since you are writing down this as a finite product of ideals, so this gives you bound. So since if you write down d of b as the product of ideals, so M1 via MK. So this gives you this tells. I mean, I haven't proved it, but what I want to say that if the case of arbitrary extension can be reduced to the case of totally ramified extension. So as we can see here, it's not completely clear, but it is just different steps of reductions, and this simply tells that Mi are larger than E minus 1. We bound Mi, so we bound so in beta, so for particular beta is larger than E beta minus 1, so that bounds E beta. So the different bounds ramification. Just the existence of such ideal as an ideal bounds the ramification indices. So let me speak now about that if you have. So how we can generate D over A? So as an algebra, the question is how we can so how to generate B over A as a module. Yeah, so notice that B is finitely generated a module. So the question is what can be taken for the basis. And now we shall discuss it. So first of all, what we shall do. So I claim that B has so it has filtration by beta I, so it has filtration by beta i's, and you see, so suppose they are all both so suppose that B and A are discrete valuation rings. A are discrete valuation rings. So this can be obtained by just localization with respect. So if you have B, the picture that the B has, so you take ideal inside A and ideal inside P, you just reduce this. So this is general case. So general case is reduced by considering B of beta, and this set contains AA, that contains localization with respect to B. So, of course, from the geometric point of view, this means that you have some beta, and localization kills all the ideals just that are outside of P, and in the same time on downstairs it also kills your ideals that do not project. So this now has filtration by P, and this is just the powers of the corresponding uniformizer. And also, so suppose you have B over beta, so this is finite extension. So you can have two cases, so you can take generators of this, so take generators of B beta. So let us call it Y1, etc. YK, YF. Yeah, because of B beta over K mod P. And then you just we get the following, so that if you have claim that B is generated so of course these are reductions, and take their representatives in P. Yeah? So lift them to Y1F in B. And so this, of course, so B, we claim that B is generated by what? By writing down Yi and the omega j. So where omega j is a uniformizer, but j is less or equal than ramification minus 1. so it comes from 0 to ramification index minus 1. And this why it is so that this follows from the variant of Nakayama lemma. So it follows. So let me formulate the required. So follows from variant of Nakayama lemma. That tells you the following, that just if M is a maximal ideal in A is a local ring, so this implies that yeah, so M and N are finitely generated modules. Then you get that if you can obtain M by adding M, the elements from ideal plus N, so then M is equal to N. So this can be applied to the following. So this variant we simply apply to just put N is equal to this set. But notice that M is now P, M is equal to P. Yeah, and for our ring, yeah, so you just, this equality will tell you that just the equality that we want to obtain, that B, yeah, so M is of course B, so we want to generate B. And this is obtained by P times B plus this generating set. And this PB is just, if you write this down, so this PB is just beta I, beta E B. Yeah, so this is just ideal beta E. Yeah, so the claim is that, so claim is that B mod beta E is generated by yi omega I, and there is omega j, and there where j is equal, less or equal than e minus 1, and the reason that you have the filtration, so this I want to prove. I'm going out of time, so explanation that it is generated by this set of elements. So since we have filtration, decreasing filtration, where factors, so where omega j, So just omega j lives inside beta I ei, beta I beta e, so beta j beta e, and generate the corresponding factor omega, generate beta j modulo beta j plus 1 isomorphic to beta j beta e modulo beta j plus 1 beta e, and this is isomorphic to a mod p times, so this is isomorphic to a mod p over the ring a mod p. It is one-dimensional module generated by omega j. So it is isomorphic to a mod p omega j. And that's, sorry, beta omega, of over beta. Yeah? And so b over beta. And b over beta is precisely so omega j generated, so this module is just b modulo beta omega j. I mean, you can just simply take the element of beta and get the element here by multiplication. So given this element, so you can map it here via, I mean, given this in b mod beta, you can map it to this factor by considering b omega j. So this means that this is one-dimensional module over b mod beta, and this implies that just from the sum of yi omega j, so generates I mean ai omega j. Yes, well, sorry, here I should say aij, yes, with some coefficients. I have forgotten coefficients. Yeah? So here, from, so ij generate, so with fixed j. So they generate beta j, beta j plus 1 over a mod p. So this implies that so each factor of the filtration is generated. So that's why all the elements together they generate the whole thing. I mean this I do not have time to explain, but this is general, just general. So a general statement. So you have the corresponding filtration, and you have the basic elements that generate each consistent factor of the filtration. So that's allows you to generate the whole space. I mean, if I mean you are just taking actually what you do, you are just taking the element. Yeah. So I mean. Maybe I should briefly explain it. So suppose you have just a general fact. So you have the sequence of modules M0 decreasing sequence M1. So M0 equal to M1. So at least you have Mn. So this is finite filtration. And suppose that you have basics of mi, ai mi, well, maybe with two indices, so such that if you fix index, so A, I, J, M, J, so so here you have the sum over AI, and here you have the sum only over I, so that generate so suppose that this generate mj modular mj plus 1. So this implies that mij generate m. And of course it is done as follows. So take element, so take m, so it belongs to, so there exists mj, so such that m belongs to mj, and so write down m in as the sum of a ij over I tilde, well, in m ij tilde so as a representative, so write down this sum in mj in the factor, and then take difference, so you will get so m minus. So for the this I mean that I'm making reduction. So take the difference of mij, and this is now element of mj plus 1, and continue by induction. By induction. And now I shall take, I shall make two reductions. So so suppose so that b over beta is separable over, so is separable over a mod p. This implies that then there exists a primitive element, alpha is primitive, so b beta is just equal to a mod p where you add alpha. A mod p where you add alpha. And this implies that b is generated by alpha I pj. Yeah, so where I is less than degree than f, and the j is less than e. Yeah, so f is the degree of this extension, and e is just the power of beta e is equal to p beta. And this is just the first reduction. So it's sufficient to prove to use two elements, but I claim that it is sufficient to use one element. So claim that we can use one element, we can use only one element. So let us find it. So suppose this is primitive and alpha, 5 alpha is equal to 0, and 5 prime is not equal to 0, not so the derivative is not identically equal to 0. So I claim the following. So suppose f of alpha is so if you take the lift, so take lift of alpha in B, yeah. So lift alpha tilde of alpha in B. So alpha of alpha tilde, this means that it is divisible. Simply it is so this is divisible by pi. Yeah. So what can be said about alpha? So alpha tilde. So alpha tilde is option 1. So alpha tilde is just a second. Yeah, so it can happen that alpha tilde is already uniformizer. Yeah. So alpha yeah. So it is, yeah. So notice that what are the options? It is divisible by p, and it can happen that f of alpha tilde is already, so f of alpha tilde is already, so a times p, yeah, so for unit a, so for so if you so it is proportional to p, so u times p for unit. Да. Поднятие альфа ну, у нас есть альфа это примитивный элемент, он внутри b фактор по бета, и вы просто его поднимаете в b. Да? Вот. И мы теперь смотрим, применяем f к альфа тильда. То есть мы видим, что вот эта штука, она делима на π. Но как бы эта степень может быть как 1, так и выше. Ну вот option 1 is that it is just divisible by, strictly divisible by p, and this means that just p is equal to f of alpha tilde, and so p tilde is different uniformizer. So this p tilde can be used as a new uniformizer, as a new uniformizer, and you can use so that means that B is generated by alpha tilde. Just because you can obtain uniformizer and you can obtain, so B is generated by the powers alpha I and pj, and pj tilde, and you can substitute this value. And option 2, so just f of alpha tilde is equal to u to p to the power k, and then you just can change, so the trick is that you can calculate f of alpha tilde plus pi. And this is just this by Taylor series. This is f of alpha tilde plus derivative of calculated at alpha. Yeah? Alpha tilde times pi plus larger degrees. Yeah. So larger powers of pi. But this has valuation. This is u to the to the power k, and this is invertible element. So f prime alpha is unit, since it is so after reduction in p reduction it is not zero in b mod beta. Yeah. So this means that so for alpha plus p you have the element with a high valuation. So this means that valuation with respect to alpha tilde plus p is just mu unit u tilde times p. Yeah, so I mean that you have p times invertible element. This thing has larger valuations. So this means that f of alpha tilde this in p. So alpha tilde plus p is equal to alpha tilde modulo beta. And so this means that alpha plus p, alpha tilde plus p reduces to alpha modulo b, and f of alpha tilde plus p is a new uniformizer, is p tilde. Is new uniformizer. So this implies that our ring beta, so B is generated by powers of p for over A for uniformizer P. Yeah, so B is so this means that B is just the sum of APIs as a module, and when simply when f is equal to 1. Yes, so alpha is just 1. Yeah, so just b. So alpha is just a unit, and so this implies that in our case that simply b is generated by p, and the degree. So by p, and the degree is less than equal to n. Yes, so that the degree of the generators I is less than equal than e minus 1. If you so in order to generate b. So this explains why we have reduced to the case when you have discrete valuation rings. And the last thing that I shall send you the file where it is explained. But this is a little bit complicated. So in order to consider general extension and to prove the formula for general extension that different is divisible, you have to decompose your extension as two extensions. One is absolutely unramified, so with E is equal to 1, and the other is ramified with totally ramified. So when you do this, this is a not non-trivial claim. So when you do this, you separately, so since you have a formula for the product of difference, you separately do the proof that for one different it is simply divisible by E minus 1. And the claim is that if you take unramified extension, then the different is trivial. So claim is when B over beta A beta this is separable, and E is equal to 1. So this means that D of A is trivial, ideal. So it's just B, I mean the whole thing. So it is as large as possible. So this product formula that tells you what happens under extensions doesn't do anything when, I mean, we are writing the large difference of C over A as a product of D of C over B and D of B over A. Yeah, so if you decompose the field as unramified and ramified, so one will be just the whole ring, and the different will reduce to totally ramified one. So that calculation of different reduces to totally ramified one. The trick is that to do this, you have to use some Galois theory, so I still need one lecture to finish, but at least so I have given you some brief explanation. So, thank you very much. Ну что, в следующий раз тогда у нас экзамен, приходите.